Turbo Compressor Control System, achieving performance, protection, and operational readiness through integrated automation. What is a Turbo Compressor Control System, TCCS? A Turbo Compressor Control System, TCCS, is a highly integrated automation framework designed to manage the safe, efficient, and reliable operation of turbocompressors, critical assets in oil, gas, and petrochemical facilities. It blends real-time control, machine protection, surge avoidance, and turbine compressor coordination under one unified architecture. Where traditional systems required separate control blocks for startup sequencing, surge protection, load sharing, and safety interlocking, modern TCCS delivers an intelligent autonomous control environment with predictive diagnostics and seamless digital interfaces. Key objectives of the TCCS: operate compression trains near their highest efficiency point without risking surge, minimize energy consumption while maximizing reliability and uptime, ensure all operations from startup to shutdown occur automatically and safely, enable easy monitoring, diagnostics, and predictive maintenance from central or remote terminals. Architectural positioning. Within the automation stack, TCCS typically operates as a dedicated modular subsystem interfacing with Distributed Control System, DCS, for high-level coordination, monitoring, and reporting. Emergency Shutdown System, ESD, for safety interlocking and shutdown responses. Fire and Gas System, FNG, for fire detection and suppression integration. Motor Control Centers, MCCs, for auxiliary motor actuation and status feedback. Condition Monitoring Systems, CMS, for vibration and temperature diagnostics. TCCS integrates these systems via hardwired and Ethernet-based, e.g. OPC-UA communications, ensuring redundancy, safety, and deterministic performance. Core functional scope of the TC: 1. Autonomous compressor train operation. Automatic startup and shutdown sequences via either the unit control panel, UCP, or external distributed control system. Real-time safety interlocks from ESD F&G systems. Maintenance mode for manual actuator testing with limited interlocks. Microprocessor-based modular architecture. Independent and fault-tolerant processors for turbine and compressor functions. Redundant communications and processing paths. Integration ready with digital twins and cloud edge supervisory layers. 3. Integrated anti-surge control, multivariable adaptive surge detection using real-time suction discharge parameters, controlled decoupling between multiple stages and trains, recycle trip logic and fallback modes upon sensor failure, real-time compressor map visualization with proximity to surge line. 4. Load sharing and capacity management, dynamic speed reference adjustment across multiple trains based on proximity to surge data. Override pressure control on suction discharge side with adjustable set points. Coordination with upstream downstream process demands via master CCP logic. 5. Turbine and fuel control. PID-based speed control with redundancy and acceleration-deceleration limits. Integration of fuel gas valve feedback and overspeed protection, triple redundant. Startup shutdown sequencing including purge, pressurization, and controlled ramp. 6. Auxiliary system management, automatic switchover for duty standby drives. Critical condition-based shutdowns triggered by support system anomalies. Continuous monitoring of seal gas, lube oil, nitrogen buffer, and filtration units. NASHFRA 7, machine protection. Vibration, thrust, and temperature monitoring via Bentley Nevada or equivalent. High-speed internal tripping logic, independent from slower serial links. Non-contact proximity probes and accelerometers with SOE sequence of events capture. 8. Human-machine interface, HMI. Real-time interactive displays for turbine, compressor, and auxiliaries. Historical trending, alarm, event review, and diagnostics. Multi-level access control for operations, maintenance, and engineering. Alarm SOE resolution within 100 milliseconds synchronized with DCS clock. Modern technologies embedded. Smart redundancy management, component-level failover with online replacement. Predictive analytics, remaining time before overhaul, RTBOH estimates, and runtime diagnostics. Integrated cybersecurity, role-based access, software authentication, and secure interfaces. Advanced trending and reporting. 30-day rolling archives with spreadsheet-style reporting and graphical overlays. Performance benchmarks. Anti-surge loop, executes in less than 50 milliseconds. Load sharing controllers executes in less than 100 milliseconds. Logic sequences, start, stop, etc. executes in 100 milliseconds. HMI update refreshes every 1 second. Graphic draw time, full graphical update within 2 seconds. Alarm SOE resolution, time-stamped within 100 milliseconds even during burst alarms. Vibration monitoring system refreshes data within 2.5 seconds. SCADA fire and gas safety integration, both water mist and CO2 suppression systems, can be incorporated. Dual voting logic via F and G inputs, 2 out of N. Local and remote initiation, override safety interlocks. Post-discharge alarms, bottle pressure monitoring and refill alarms. Skid integrated actuator and bottle control systems. System condition feedback on UCP and to F and G control system. Reliability, availability, and maintainability, RAM. Minimum system availability of 99.9%. Fault-tolerant design with calculated mean time between failure, MTBF, and mean time to repair, MTTR, not exceeding 24 hours. Fully online maintenance, software updates, controller tuning, and card replacement without shutdown. Modular diagnostics down to channel-level faults, supported by context-sensitive HMI help. The Turbo Compressor Control System TCCS represents a next-generation leap in asset protection, process performance, and operational intelligence. By embedding surge prevention, predictive diagnostics, turbine governor integration, and auxiliary control into a unified modular architecture, the TCCS minimizes downtime, improves efficiency, and enables semi-autonomous operation. With support for hybrid modeling, OPC communications, and advanced condition monitoring, modern TCS systems ensure compressor trains run closer to constraints, safely and efficiently. As industry demands evolve toward digitized, resilient, and environmentally accountable operations, the TCCS stands as a foundational pillar of high-performance compression management. Topographical structure of the Turbo Compressor Control System, ensuring modular integrity, signal redundancy, and system interoperability. Topography of the Turbo Compressor Control System. The Turbo Compressor Control System TCCS is designed with a modular and distributed architecture, ensuring seamless integration across multiple compressor trains and delivering high resilience, maintainability, and flexibility for future expansion. The system's layout separates compressor-specific and shared functionalities while maintaining robust intercommunication and unified operational coordination. Core components of the TCCS architecture. Unit control panels, UCP. Each turbo compressor train is assigned a dedicated unit control panel. These enclosures manage all critical control and protection functions associated with that specific compressor. UCPs include anti-surge and load sharing controllers, startup and shutdown sequencing, turbine and auxiliary control, local HMI access, and embedded machine diagnostics. Common Control Panel, CCP. The CCP acts as the supervisory hub coordinating across all compressor trains. It manages master pressure control logic, orchestrates intertrain load sharing, and handles plant-wide communications with external systems such as the Distributed Control System DCS, Emergency Shutdown System ESD, and Fire and Gas F&G safety infrastructure. Redundant high-speed communications backbone. Communication between the UCPs and CCP is handled via a high-speed, fault-tolerant digital bus. This network is fully redundant and ensures deterministic performance across all control, protection, and coordination layers. It provides data exchange for compressor health, control set points, alarm management, and event synchronization. Functional subsystems integrated within the TCCS. Turbine control including startup, shutdown, fuel control, speed regulation, and overspeed protection. Compressor performance optimization with real-time efficiency calculations and operating point supervision. Compressor anti-surge protection with dynamic proximity calculation to surge line. Recycle and capacity control using coordinated valve actuation logic. Load sharing across parallel compressor trains using surge margin-based control distribution. Suction pressure and discharge pressure override control for safety-critical boundaries. Auxiliary system monitoring such as lube oil, seal gas, and nitrogen buffers with automated failover logic. Vibration, displacement, and temperature-based machine protection with high-speed internal trip logic. Operator HMI interface for local diagnostics, trend visualization, manual overrides, and maintenance support. Communication and hardwired interlocks to DCS, ESD, MCCs, and CMS platforms. Integration and segmentation principles. Each control panel, UCP and CCP, is a standalone enclosure with independent power supply and processor logic, enabling isolation of faults and enhancing system maintainability. The distributed nature of the system ensures that a fault in one panel does not propagate to other parts of the system. Physical layout is optimized to minimize wiring complexity, reduce electromagnetic interference, and facilitate safe maintenance access. Control, monitoring, and protection functions are physically and logically segmented to meet failsafe and safety integrity level SIL requirements. Support for advanced digital integration. The architecture is compatible with modern control philosophies including digital twin simulation, cloud edge optimization layers, and machine learning predictive diagnostics. Communication architecture supports deterministic protocols such as Modbus TCP/IP, OPC UA, and redundant Ethernet for secure plant-wide data exchange. Time synchronization with the DCS master clock ensures accurate sequencing and event correlation across all subsystems. This topographical strategy ensures that the TCCS remains scalable, robust, and adaptable to evolving performance and safety requirements while supporting modular redundancy and digital innovation. Hashtag redundancy of the Turbo Compressor Control System, enabling high availability through fault-tolerant architecture and graceful degradation. Redundancy of TCCS. The Turbo Compressor Control System TCCS is engineered with an inherent focus on maximizing system availability, minimizing downtime, and ensuring safe operation even in the event of hardware, sensor, or power-related failures. Redundancy is embedded across all critical components of the system to meet high availability targets, typically 99.9% or better, as required for continuous process industries. Redundancy philosophy. Redundancy is applied selectively across components based on the criticality of the function and failure impact on compressor operability and safety. Fault tolerance is achieved through logical fallback mechanisms, duplicate inputs, and strat modular fault containment, ensuring continuity of control and machine protection even when certain failures occur. Formal system availability calculations, supported by mean time between failure (MTBF) and mean time to repair (MTTR) estimates, guide the design and validation of the redundancy scheme. Field instrument redundancy strategy. Most field sensors are installed in simplex configuration to reduce complexity and cost. Critical process variables are measured using duplicated or triplicated sensors, especially for fuel gas pressure, machine rotational speed, lubricating oil pressure, seal gas pressure, nitrogen buffer pressure. Sensor voting logic within the unit control panel, UCP, is implemented to detect discrepancies between signals, raise deviation alarms upon detection of faulty sensors, allow safe continued operation using the remaining good sensors, where hot swapping is possible. Controller and I/O redundancy. TCCS processor modules, power supplies, and communication interfaces are designed with N+1 or dual redundancy, allowing hot standby switching with no control interruption, online replacement of failed modules without shutting down the machinery, continuous heartbeat monitoring and auto-swapping logic for failed channels or processors, manual override and operational continuity. In control instances where failure of a control input may impact compressor performance but not compromise safety, manual override functions are provided. Operators may switch to manual mode to maintain operations in scenarios such as load-sharing controller failure, master pressure controller failure, anti-surge fallback due to signal loss, alarm and deviation handling. All redundant sensors are monitored for signal integrity. Alarms are raised in the human-machine interface, HMI, and DCS in case of sensor disagreement, communication failure, processor or I/O malfunction. SOT panel-level redundancy and isolation. Loss of power or logic within one compressor's UCP causes shutdown of that specific compressor only. Other trains continue to operate unaffected due to panel-level isolation. Loss of the CCP disables supervisory-level coordination, e.g. load sharing, master pressure control, but each UCP reverts to independent autonomous operation using the most recent valid set points. This approach ensures that the TCCS maintains graceful degradation under failure conditions, preserving core safety and critical control while isolating faults to prevent systemic disruptions. The result is a resilient, highly available control infrastructure suitable for mission-critical compressor applications. Failsafe design, programmability, and operational modes of the TCCS, embedding operational security, code maintainability, and human oversight into system-to-fail-safe circuits. The Turbo Compressor Control System, TCCS, prioritizes fail-safe behavior across all control and interlock pathways to guarantee personnel safety, equipment protection, and process containment, even during power loss, hardware failure, or abnormal conditions. Core fail-safe principles. All digital inputs, outputs, and logic circuits are designed such that energized represents a healthy or normal state. De-energization of a control line or relay coil initiates safe shutdown or protection action. Control output logic ensures that loss of signal equates to a command to trip, close, or stop, never to continue operation. Power loss behavior. Loss of power to a unit control panel, UCP, results in a controlled shutdown of the associated compressor train. Other compressor trains remain operational and unaffected. Loss of power to the common control panel, CCP, leads to loss of central coordination, but UCPs maintain automatic local control using the last known valid set points. Hardwired shutdown assurance. All shutdown commands from emergency shutdown system, ESD, fire and gas F&G system, or manual push buttons are transmitted via hardwired volt-free contacts, not over serial links. This ensures shutdown commands are executed immediately and independently of any communications faults or software delays. The TCCS is built around a modular, user-friendly programming environment that supports structured logic development, clear documentation, and seamless maintenance, even during live operation. Programming environment characteristics. The programming tool supports structured programming standards conforming to IEC 61131 guidelines. Logic is written in intuitive languages such as function block diagrams, FBD, sequential function charts, SFC, ladder logic diagrams, LD, structured text, ST. Documentation and commenting. Every logic block and sequence includes inline comments, cross-references, and signal traceability for rapid understanding. Change tracking and version history tools ensure that all modifications are auditable. Change management and diagnostics. Self-documenting code architecture allows for identification of logical root causes for faults, easy implementation of new logic sequences or equipment additions, real-time debugging with online variable watching, value forcing, and diagnostic flagging. Software tools and support. The vendor provides all necessary software licensed to allow both online and offline configuration. Programming, diagnostics, and reporting tools are available through graphical interfaces with drag and drop and hierarchical navigation support. Control modes. The TCCS supports multiple modes of operation for each compressor train, providing operational flexibility, supervisory control, and maintenance override options, all with safe interlocks. Mode selection via hardwired panel switch. Each UCP is fitted with a 3-position master mode selector switch. Local mode. Control from the UCP's human-machine interface, HMI. The external distributed control system, DCS, is in monitor-only mode. Operators can manually initiate start-stop and observe real-time data. Remote mode. Control from the external DCS. The UCP HMI is limited to monitoring. No control actions are permitted. All interlocks and trip functions within the UCP remain active and autonomous. Maintenance mode, used during shutdowns or when testing actuators and I/O without full machine interlocks, disables protection sequences selectively for manual equipment actuation. Selecting this mode while running immediately initiates a controlled shutdown. Cannot be selected directly when switching between local and remote, requires intermediate stop. Bumpless transfer. Transition between local and remote modes is smooth and bumpless, ensuring no sudden set point shifts or operational disturbances. The master selector switch status is continuously visible on both the UCP HMI and DCS to maintain operator awareness. DCS monitoring across modes. Regardless of the active control mode, the external DCS maintains full visibility of process variables, alarm and event logs, mode selector switch position, status of actuators, and shutdown initiators. This flexible, layered control mode strategy allows the TCCS to support autonomous operation, centralized oversight, and safe manual intervention, all within a robust safety framework.